Welcome to Unraveling Infinity's Code, where we dive headfirst into the biggest questions of the universe. From Einstein's warped spacetime to Wolfram's idea of a cosmic computer, we're cracking open the secrets of existence. Join us as we explore the structures that shape everything: space, time, even consciousness. Buckle up, keep your mind open, and let's unravel the mysteries together.
Welcome back. Remember our last deep dive, the one with the Majorana fermions, and how they might be connected to the Riemann hypothesis.
Yeah, those were some pretty complex ideas.
For sure. It really got me thinking about infinity and the challenges of extending these systems to infinite dimensions.
Yeah, that's a real head scratcher. Has been for a long time.
Totally. And speaking of infinity, you sent me some research on that. That approaches the idea from two totally different perspectives. It looks at Einstein's idea of infinity as continuous, and then Wolfram's computational approach, which is like discrete. It's almost like they're speaking different languages.
It is really interesting how they come at it from such different angles. It's like mixing oil and water.
Yeah.
Right. But this analysis tries to find some common ground between them, see if there's a way to bridge the gap.
Okay, so let's break this down. First up, we've got Einstein and his idea of continuous infinity. Can you maybe walk us through how he thought about infinity, especially like in the context of his work on space and time?
Einstein's understanding of infinity is like deeply woven into his theory of general relativity. He basically pictured space-time as this continuous fabric,
Okay.
like a giant sheet that can be bent and warped by like mass and energy.
So that's where gravity comes in, right? It's the warping of this space-time fabric that we feel as gravity.
Exactly. To help visualize this, imagine you're trying to measure a circle that's drawn on the surface of a sphere.
Okay.
What you'll find is that the classic formula for a circle's area, pi times the radius squared, it doesn't quite work anymore.
Wait, why not? That formula is burned into my brain from high school geometry.
It's because on a curved surface, like a sphere, the relationship between distance and dimension gets a little weird. As the circle gets bigger and bigger on the sphere, the curvature becomes more and more important.
Okay, I think I see what you mean. Yeah.
So to get the area, you have to adjust the formula to account for that curvature. And that brings us to a different kind of infinity than what on a flat surface.
So even though the sphere's surface area is finite, the way it curves creates a different kind of infinity. Like infinity isn't just about quantity, but about the structure of space itself.
You got it. And this whole concept of curvature is like super fundamental to how Einstein's theory of general relativity describes like the universe on a grand scale.
Okay, so that's Einstein's smooth continuous infinity.
Yeah.
Now let's jump over to Wolfram's side of the court. He's got a very computational approach to understanding the universe, right?
Absolutely. Wolfram sees the universe through the lens of computation and these things called discrete structures. His theory is that the universe is basically like a giant computer program built from simple rules that when you repeat them over and over, generate all the complexity we see.
So like a cosmic computer program is running in the background of everything.
In a way, yeah. Wolfram's model uses structures called hypergraphs. They're like networks with nodes and connections, but way more complex. He argues that like the evolution of the universe can be thought of as a series of computations done on these hypergraphs.
Okay, I'm intrigued. But where does infinity fit into this whole computational model?
It ties into this idea called causal invariance. Basically, it means that the order you do operations in a computation doesn't change the final outcome.
Oh, like in algebra?
Like solving an equation, you can rearrange the terms however you want, but you'll always get the same answer in the end.
So there could be like multiple paths to the same result. That's cool.
Exactly. And what's even cooler is that this idea of causal invariance seems to connect directly to both special relativity and quantum mechanics. So even though Wolfram's model is all about these discrete structures, it naturally leads to concepts that we normally think of as being part of continuous spacetime.
Now that's what I call mind-blowing. We're talking about two totally opposite views of infinity somehow converging. But how do we actually bridge the gap between Einstein's continuous spacetime and Wolfram's discrete computations? Is that where this whole digit-level abstractions thing comes in?
You got it. Digit-level abstractions might be a way to connect these seemingly incompatible ideas. Imagine instead of thinking of particles as these tiny points in space, we think of them as little lumps of space within Wolfram's hypergraph.
Little lumps of space. I like that. So it's not just a point in a location, but the structure itself that defines the particle.
Exactly. The specific properties of each particle, like its mass or charge, would be determined by its structure and how it's connected within the hypergraph.
Okay. I think I'm starting to get it, but where does quantum mechanics fit into all of this? And what about these big mysteries of the universe, like dark matter? It feels like this new framework might have something to say about those too.
What's really fascinating is the potential link between quantum phenomena and number theory. This model suggests there could be these particles called oligons, particles made up of just a few hypergraph elements.
Oligons from oligo, meaning few. So because they're made of just a handful of these fundamental elements.
And because of their unique structure, these oligons would interact very weakly with all the other matter in the universe.
So they'd be like cosmic ghosts, difficult to detect, but still out there potentially influencing things in subtle ways.
Precisely. They might have been produced in huge numbers in the early universe, but because of those weak interactions, they would drop out of thermal equilibrium, basically becoming relics from a long time ago.
And these relics, could they be the elusive dark matter we've been searching for?
It's a really exciting possibility. While they'd be incredibly difficult to detect directly, they could still contribute to the universe's overall mass and influence its gravitational dynamics. It's definitely a promising avenue for future research.
Wow, we've gone from two contrasting views of infinity to potentially explaining dark matter. What a journey. What's the biggest takeaway here? What's the key point for our listeners?
I think the most mind-blowing concept here is how this analysis changes our understanding of infinity itself. We usually think of infinity as this vast, unending quantity. But this research suggests that infinity is more about structure, the underlying architecture of reality.
Structure over quantity. It's not just about how much of something there is, but about how it's all arranged and interconnected, like that sphere example, right?
Exactly. The sphere has a finite surface area, but the way it curves creates a different type of infinity compared to a flat plane. It's a profound shift in perspective, and it could revolutionize how we approach some of the biggest questions in physics and cosmology.
All right, so we've dug into Einstein's and Wolfram's views of infinity and explored this potential bridge between them using digit-level abstraction. You also sent over some research on Goldbach's conjecture, a famous unsolved problem in number theory. What does that have to do with all of this?
This is where we see the concept of structure playing out in a totally different but equally fascinating way. Goldbach's conjecture states that every even number greater than 2 can be expressed as the sum of two prime numbers. The research you sent dives into this conjecture using computational methods to try and find patterns and hidden structures within prime numbers.
So basically crunching numbers to see if Goldbach was onto something. What did they find?
The research supports Goldbach's conjecture, but it also uncovered something really unexpected. There's a hidden structure in how prime pairs are distributed. They found that certain even numbers they call Goldbach champions have a way higher number of prime pairs that add up to them.
It's like they're winning some kind of cosmic prime number lottery.
Haha, exactly. It's like these even numbers have a special magnetism for prime pairs.
So it's not just random scattering of primes. There are patterns at play here.
Yes. And the research gets even deeper. They looked at the specific arrangement of odd and even digits within prime numbers and how that arrangement affects their pairing behavior. They call this digit composition analysis.
So each prime number has a unique fingerprint based on its digits, and those fingerprints determine how the primes interact with each other to form those Goldbach pairs.
That's a great way to put it. And this analysis revealed non-random patterns and these numerical fingerprints in how prime pairs are distributed. It further supports the idea of emergent structure within prime numbers.
This is amazing. So we have these two seemingly separate topics, the nature of infinity and the hidden structure of prime numbers. But are they truly separate? Could there be some deeper connection between them?
That's the million-dollar question. Remember how the analysis of Goldbach's conjecture revealed a kind of hidden social structure within prime numbers? It's not just about quantity, it's about relationships and patterns. And that same concept of structure, as we just discussed, might be the key to understanding the true nature of infinity itself.
Wow, that's deep. So even though we started with two different topics, there's this common thread running through them both. Yeah. A shift in focus from quantity to structure. Like we need to change how we see the universe.
You got it. And that shift in thinking might just unlock new insights into the fundamental nature of the universe and everything in it. It's incredible how these abstract mathematical ideas like infinity and prime numbers could be connected in ways we're just starting to understand.
I know, right? It's like we're getting a glimpse behind the scenes of reality, peeking at the code that makes the universe work.
That's a great way to put it. And one of the coolest things about Wolfram's model is that it doesn't actually need the idea of infinite dimensions in the traditional sense.
Really? But we were just talking about how hard it is to extend those systems to infinity.
I know, right? But in Wolfram's model, instead of needing infinite dimensions, we have this concept of branchial space.
Branchial space. Okay, you're going to have to explain that one. Sounds a bit like science fiction.
Think of it this way. Every time a computation happens in Wolfram's universe, it creates a new branch of possibilities. Imagine a tree with tons of branches, each one representing a different outcome of a computation.
So it's not about physical dimensions like we usually think of them, but more about the potential for different computational paths to unfold.
Exactly. This branchial space allows for all the complexity and richness we see in the universe without needing the idea of infinite physical dimensions. It's like the universe is constantly exploring different possibilities through these computational branches.
Okay, I'm starting to see how Wolfram's model gets around that whole infinite dimension problem.
Uh-huh.
But how does this branchial space connect to quantum mechanics? You mentioned a link earlier, and I'm curious to hear more.
This is where things get really interesting. In quantum mechanics, we have this crazy idea of superposition, where a particle can be in multiple states at the same time until we measure it.
Like Schrodinger's cat,
Oh,
both alive and dead until we open the box. It makes my head spin.
exactly. Now, in Wolfram's model, moving through branchial space is like making a quantum measurement. Each branch represents a possible outcome, and when we choose a branch, it's similar to collapsing the wave function in quantum mechanics, forcing the particle into a single state.
Hold on, are you saying that our choices, our actions in the real world, are somehow equivalent to navigating this abstract computational space? That's a wild thought.
It's a bold idea for sure, and there's a lot we still don't know. But the similarities between Wolfram's computational universe and the weirdness of quantum mechanics are definitely something to think about. It makes you wonder about the role of consciousness and free will in shaping reality.
I'm trying to wrap my head around this. It's like our choices are somehow shaping the fabric of reality by selecting certain computational paths. It's a lot to take in.
It is a fascinating concept, isn't it? It challenges us to rethink what we think we know about reality and how the observer and the observed are connected.
Let's shift gears for a second and bring things back down to earth. You mentioned this digit composition analysis earlier, which revealed numerical fingerprints in prime pairs. Can you give us some concrete examples of what these fingerprints look like? I'm having trouble picturing it.
Sure, researchers discovered that the specific arrangement of odd and even digits within a prime number actually affects how likely it is to pair up with another prime number to form a Goldbach partition.
Okay, so how does that work? What's the connection between the digits in a prime number and its pairing behavior? It seems like those should be totally unrelated.
It's not that the digits themselves have some magical property, it's more about the patterns they represent.
Patterns. What kind of patterns are we talking about here?
For example, they found that prime numbers with more odd digits than even digits tended to pair up more often with prime numbers that had more even digits than odd digits. It's like there's a balancing act happening.
So prime numbers with extra odd digits are looking for prime numbers with extra even digits to create some kind of harmony, like they're trying to achieve balance in the prime number world.
That's a great way to visualize it. It's as if there's a built-in preference for certain digit combinations within prime pairs.
Wow, that's amazing. It's like we're uncovering a secret language within numbers, a language that controls how they interact and relate to each other.
And the more we understand this language, the more we might uncover about the fundamental structure of mathematics, and maybe even the universe itself.
Okay, so we've explored this digit composition idea and how it reveals patterns in prime pair distributions. But where do we go from here? What does this tell us about the bigger picture?
What's really cool is that we're seeing another example of struction emerging from what seems like random noise. The distribution of prime numbers has always seemed unpredictable, but this digit composition analysis suggests there's an underlying order, a hidden blueprint guiding their arrangement.
It's like those magic eye pictures. You have to relax your eyes and look at the random dots to see the hidden 3D image.
Exactly. And just like with magic eye pictures, the more we study the patterns in prime numbers, the more we might reveal a deeper multidimensional reality that's been hiding in plain sight.
That's a great analogy. But how does this all tie back to infinity, the idea we started with?
Remember how Einstein's continuous infinity is tied to the curvature of space-time? In a way, this digit composition analysis is showing us a different kind of curvature, a curvature within numbers themselves.
A curvature of numbers. That's wild. But I think I see what you mean. It's the distribution of prime numbers isn't flat or random. It's bending and twisting in ways we're just beginning to map. Like the curved surface of that sphere we were talking about.
Exactly. And just like the curvature of space-time affects how objects move in the universe, this curvature of numbers might be shaping how prime numbers interact and influencing the overall structure of mathematics. It's a mind-boggling concept, but it shows how connected these different areas of study might be.
Okay, my brain is officially doing backflips. So we're seeing connections between infinity prime numbers, quantum mechanics, and even the nature of reality itself. It's like we're pulling on a thread and unraveling a cosmic tapestry.
And here's the kicker. The research you sent over also hints at a possible link between this digit composition analysis and the mystery of dark matter.
Wait, dark matter again. How does that fit in?
Yeah.
We've gone from infinity to prime numbers to quantum mechanics. It's hard to imagine how dark matter could be related.
It's still a very speculative idea, but the researchers think that certain patterns in prime pair distributions, especially those connected to those Goldbach champions we talked about, might point to particles that interact very weakly with regular matter.
So you're saying these prime number patterns, these numerical fingerprints, could be a clue to dark matter's existence, like they're leaving a trace of themselves in math.
It's a bold idea, and it needs a lot more research. But it highlights the potential for unexpected connections between different areas of study. Sometimes the biggest insights come from thinking outside the box and looking for patterns in unexpected places.
This is all so fascinating. We've covered so much ground in this deep dive, and I feel like we're just scratching the surface.
That's the beauty of exploration, isn't it? The more we learn, the more we realize how much more there is to discover. The universe is full of mysteries, and it's up to us to figure them out.
Welcome back. I don't know about you, but my head is still spinning from all that. It's like my brain did a marathon.
I hear ya. It's a lot to take in, but that's what makes these conversations so much fun. We're going where no one has gone before, pushing the limits of what we know, and that's where the really cool stuff happens.
Absolutely. So let's get back to this crazy idea that there could be a link between dark matter and patterns in prime numbers. Seems like such a stretch. How can something as abstract as numbers relate to the physical universe?
It all goes back to that idea of structure that keeps popping up. Remember, both Einstein and Wolfram's models suggest that the universe is more about structure than just quantity.
Structure over quantity, I get that. But I'm still having trouble seeing how that connects to dark matter.
If dark matter really exists, and there's a ton of evidence that it does, it must have some kind of structure. It can't be just a shapeless blob hanging out in the universe. It must interact with itself somehow, and it might even be made up of many different types of particles, each with its own special properties.
So are you saying that the structure of dark matter, whatever that is, might be reflected in other structures? Like the patterns we've been talking about in prime numbers. Yeah. Like looking at a reflection in a pond, right? We can learn about the object by looking at its reflection.
That's a really great way to put it. It's like how we can learn about the structure of a crystal by studying the patterns it creates when light shines through it. We can learn about the hidden structure of something by looking at how it interacts with other things.
I was also really interested in how this deep dive contrasts two very different ways of looking at infinity.
It's almost like two opposite sides of the same coin.
Yeah, exactly. And it seems like Wolfram's ideas have been getting a lot of attention lately.
And Wolfram's point is that the universe itself might be like a giant computer.
So instead of a smooth, continuous space-time, we have this universe that's made up of discrete bits of information, like the pixels on a computer screen.
Exactly.
That's incredible. And I think that's where it starts to get really mind-blowing, because the researchers didn't just stumble upon these Goldbach champions by chance. They use a technique called digit composition analysis.
That's what makes this research so intriguing. They're not just looking at the primes themselves, but also at the patterns in their digits.
And what's really wild is that they found that the specific arrangement of odd and even digits within a prime number somehow influences its Goldbach richness.
It's almost like there's a hidden code within the primes, a kind of secret language that governs their behavior.
It's like those old mystical ideas about numbers having magical properties.
Yeah.
But now we're starting to see that there might actually be some truth to that.
Yeah, it's really fascinating, and it suggests that there's a lot more to prime numbers than we ever imagined.
Okay, so we've got this idea that the arrangement of digits within prime numbers somehow influences their behavior.
I think this is where Wolfram's ideas start to come into play. So what if these patterns we're seeing in prime numbers, these Goldbach champions and digit compositions, are actually giving us a glimpse into those computational rules?
Whoa.
It's a possibility, and I think it's one worth exploring.
I'm completely on board with that. So let's dive into Wolfram's model in more detail. We've touched on the basics, but I want to understand, what's a hypergraph?
Think of it like a network of interconnected points. But unlike a regular graph, where each connection links only 2 points, a hypergraph can have connections that link any number of points.
Oh, I see. So it's like a much more complex and interconnected kind of network.
Exactly. And in Wolfram's model, each point in the hypergraph represents a fundamental element of reality. He doesn't specify exactly what these elements are, but you can think of them as something like the most basic building blocks of existence.
Okay, I'm following you. So we've got these points representing the fundamental elements of reality, and then the connections between them represent the rules governing how these elements interact.
Yeah, you got it. And the whole universe, according to Wolfram, is just this giant, evolving hypergraph.
So instead of smooth, continuous spacetime, we have this discrete network of interconnected elements, like a cosmic Lego set.
Yeah, that's a good analogy. And the really cool thing is that even though the hypergraph is made up of discrete elements, the overall behavior of the system can still be smooth and continuous, just like how a digital image, even though it's made up of pixels, looks smooth to us.
Okay, that makes sense. But how does he explain things like the curvature of spacetime, which is so central to Einstein's theory of relativity?
That's where the concept of causal invariance comes in.
Causal invariance. I'm intrigued. Tell me more.
It's a mouthful, but essentially it means that the order in which events happen within the hypergraph doesn't affect the final outcome.
So even though the underlying processes are happening in discrete steps, the overall picture is still consistent.
Exactly. And that's how Wolfram reconciles his discrete computational model with the seemingly continuous nature of spacetime.
It's like saying that even though a movie is made up of individual frames, we still perceive it as a smooth, continuous flow of images.
That's a great analogy. And it highlights how emergent properties can arise from complex systems, even if those systems are built from simple rules.
Okay, so we've got this discrete computational universe built on a hypergraph, with causal invariance ensuring that it's consistent with our observations of spacetime. But where does infinity fit into all of this?
Ah, yes, infinity. That's where things get really interesting.
You've certainly piqued my curiosity. What's Wolfram's take on infinity?
He proposes a different kind of infinity than what we usually think of. He calls it computational infinity.
Computational infinity? I've never heard that term before.
Think about it this way. The hypergraph is constantly branching, creating new connections and new possibilities as it evolves.
Like a tree constantly sprouting new branches, reaching out in all directions.
Exactly. And Wolfram proposes that this branching process continues infinitely, creating a vast space of computational possibilities. He calls this space branchial space.
So instead of infinite space or time, we have this infinite realm of branching computational paths. It's like the universe is constantly exploring all possible outcomes of its own rules.
That's the essence of Wolfram's idea of computational infinity. It's not about endless physical dimensions, but rather about the endless potential of computation.
Wow, that's a profound shift in perspective. And it makes me wonder if the nature of infinity itself might be more about potential than about actuality.
It's a thought-provoking idea for sure.
It definitely is. And it leads us to some really intriguing connections between Wolfram's model and the mysteries of quantum mechanics, which we'll talk about next.
Yeah, the quantum realm is where things get even weirder.
Oh, I can't wait. We've been talking about this idea of a computational universe and how it could change the way we think about everything from infinity to the laws of physics. But I think one of the most exciting things about this model is that it offers some potential solutions to some of the biggest mysteries in science.
Yeah, I agree. For example, dark matter.
Dark matter, it's this invisible stuff that makes up like 85% of the matter in the universe.
Yeah, and we know it's there because of its gravitational effects on galaxies and stuff, but we have no idea what it actually is.
It doesn't interact with light or any other kind of electromagnetic radiation that we know of. So it's like this invisible ghost that's holding the universe together.
Exactly. And that's where Wolfram's model comes in. He actually proposes a candidate for dark matter based on his computational universe idea.
Oh, really? What is it?
He calls them Oligons.
Oligons. That's a cool name. So what are they?
They're not like the fundamental particles that we know of, like electrons and quarks and stuff. Instead, they're like emergent particles that arise from the hypergraph itself.
Okay, so they're not like little tiny balls of matter, but rather patterns of information in the hypergraph.
Exactly. Think of them as these little pockets of complexity within the hypergraph, and they behave in ways that are different from the other elements in the hypergraph.
So they're like these little mini universes within the larger universe.
Yeah, you could think of it that way.
And how do these oligons explain dark matter?
The idea is that oligons interact very weakly with the other elements in the hypergraph, so they would be very difficult to detect directly, just like dark matter.
Oh, I see. So they're like ghosts in the computational machine. They're there, but they're not really interacting with anything.
But even though they're not interacting much, they still have mass, and that mass would contribute to the overall gravity of the universe.
So that's how they explain the gravitational effects that we see from dark matter. It all makes sense now.
And what's even cooler is that Wolfram thinks there might be a connection between oligons and prime numbers.
Oh, yeah. You mentioned that earlier. How do those two things relate?
Remember how we were talking about those patterns in Porter numbers, like the Goldbach champions and the digit composition stuff?
Yes.
Wolfram suggests that those patterns might actually be a reflection of the underlying structure of dark matter.
Whoa. Hold on. You're saying that the way prime numbers are arranged could be like a fingerprint of dark matter.
That's the idea. It's a pretty wild idea, I know.
It's definitely wild. But it's also incredibly exciting. We're looking for clues about the nature of dark matter in the patterns of prime numbers.
Yeah, it's like those patterns are like a secret code that we need to crack in order to understand the universe.
Like a cosmic treasure hunt.
Exactly.
Okay, but if Wolfram is right, what are the implications for our understanding of dark matter? Could we actually use this information to detect it or even study it in new ways?
That's a good question, and I think it's still too early to say for sure. But if there really is a connection between prime numbers and dark matter, then it could open up whole new avenues for research.
Yeah, like maybe we could design experiments to look for specific patterns in prime numbers that would tell us something about the distribution of dark matter in the universe.
Or maybe we could even use our knowledge of prime numbers to develop new technologies for interacting with dark matter.
Whoa, now we're talking like dark matter engines or something.
Yeah, who knows? It's definitely a possibility.
This is all so fascinating. I'm really glad we're having this deep dive.
Me too.
Okay, so we've covered a lot of ground on dark matter. I also wanted to talk about another mind-blowing idea that you mentioned earlier, which is the potential for quantum computers to interface with the universe's code.
Oh, yeah, that's a really exciting area of research.
Yeah, it's like straight out of science fiction.
It is, but some very serious scientists are working on it.
So tell me, how would that even work?
The idea is that if the universe is fundamentally a quantum computation, then maybe we can build a quantum computer that's designed to resonate with that underlying structure.
So it's not just about building a really powerful computer, but also about building it in the right way, the right kind of architecture.
Exactly. And some people believe that the key to doing that might lie in the Riemann hypothesis.
Oh, the Riemann hypothesis. That's another one of those famous unsolved problems in mathematics, right? Something about the distribution of prime numbers.
Yeah, that's the one. It's a really deep problem, and it's been around for over 150 years.
So how could the Riemann hypothesis help us build a quantum computer that can interface with the universe's code?
The Riemann hypothesis is all about the zeros of a certain mathematical function called the Riemann zeta function. And these zeros are thought to be somehow related to the distribution of prime numbers. So the idea is that if we can build a quantum computer that's designed to take advantage of the properties of the Riemann zeta function, then maybe we can use it to tap into the universe's underlying computational structure.
So it's like we're building a quantum computer that's tuned to the same frequency as the universe.
Exactly. And if we can do that, then who knows what we might be able to achieve.
It's almost like we're talking about magic at this point.
It does sound like magic, doesn't it? But it's actually based on some very solid math and physics.
The idea of a computer that can interact with the fabric of reality is pretty mind-blowing.
If the universe really is a computation, what does that mean for us? What does it mean for the nature of reality, the nature of consciousness, the meaning of life?
Those are some big questions.
They are, but I think they're questions that we need to be asking if we want to truly understand our place in the universe.
I completely agree with you. This has been an amazing deep dive. I've learned so much, and I'm sure our listeners have too.
I've had a great time.
Me too. And I think it's clear that Wolfram's model of computational universe is one of the most exciting and thought-provoking ideas to come along in a long time.
I agree. It's a real game changer.
Okay, but what about consciousness? Where does that fit into a computational universe?
That's another big one. And again, I don't think there's a single answer that everyone agrees on.
Yeah, consciousness is still pretty mysterious, even in our current understanding of the universe.
Absolutely. But one possibility is that consciousness is an emergent property of computation.
Emergent property. What do you
Okay.
mean by that?
It means that consciousness isn't something that's explicitly programmed into the system. It's something that arises spontaneously from the complexity of the computation itself.
So it's when you have a bunch of simple parts interacting with each other, sometimes something new and unexpected emerges.
Exactly. Think about the human brain. It's made up of billions of neurons, each of which is a relatively simple cell. But when all those neurons interact with each other, you get consciousness.
So maybe consciousness is like that. It's a product of the incredible complexity of the universe's computation.
That's one possibility.
But if that's true, does that mean that our thoughts and feelings are just illusions?
I don't think so. Even if our thoughts and feelings are ultimately the product of computation, that doesn't make them any less real.
It's like saying that the beauty of a sunset is an illusion just because we understand the physics of how light works.
Exactly. The experience is still real, even if we understand the underlying mechanisms.
Okay, that makes sense. But there's still this question of meaning. If the universe is a computation, does that mean there's no point to it all?
I think that's a question that each individual has to answer for themselves. But I don't think the fact that the universe might be a computation necessarily takes away from its meaning.
Because even if there's no inherent meaning, we can still create our own meaning.
Exactly. We can still choose to live our lives in a way that is meaningful to us.
Okay, this has been a really thought-provoking conversation.
Yeah, it's been great.
We've covered a lot of ground, from prime numbers to dark matter to the philosophical implications of a computational universe. And I think it's clear that there's still so much that we don't know.
Absolutely. But that's what makes it so exciting.
I agree. So thank you so much for joining me on this deep dive.
My pleasure.
And to all our listeners out there, thank you for coming along for the ride. We hope you've enjoyed this exploration of the computational universe. Keep those minds open, and we'll see you in the next deep dive.